Okay, so let's talk now about polynomial functions. Now here we're just gonna brief through this idea because in pre-calculus that's when you actually study these functions in general. Okay, so quadratic functions, they are a particular case of polynomial functions and lines as well. You know everything about lines. Now you know everything about quadratic functions. But in general, polynomial functions, they're a little bit more involved, a little bit more complicated. We're just going to get the main ideas and look at some easy cases. When I say easy cases, what I really mean is the hard part about polynomials is being able to factor. Okay? So once you have a polynomial factor, once you know the zeros of the polynomial, then it's very easy to sketch the graph and answer questions about them. Okay? But to actually find the zeros, in general, this requires some work. So to factor polynomials, and in pre-calculus, you learn techniques about that. Okay? The examples that we're going to do, our polynomials will either be already factored, okay, or will be very easy to factor, so we can answer the question. This is just so you get the general idea. The most important thing that I want you to be able to do is, given a polynomial, let's say already factored, or with the zeros information, how do you graph it? Okay, how do you sketch the graph of polynomial? But it's easier than all the stuff that I'm about to say, but I have to write some things just for formality's sake and to make sure that everybody understands what we're talking about. So the first thing is, what's a polynomial function? So you need to be able to look at a function and say, this is a polynomial, this is not a polynomial. Okay? Now, what I'm about to write will look a little slightly complicated maybe for some of you, but it's actually very easy. So once we do an example, you will see it's very straightforward. Okay? But anyways, here is the formal definition. So a polynomial function is an expression of the following form. So it's an expression that can be written in the form, and then let's see, I call it P of x, P for polynomial, and then an x to the n plus an minus 1, x to the n minus 1, and so on, plus a1x plus a0. So these a's are right here, this n minus 1, n minus 2, n minus 3, all the way down to 0. This is just an index, okay? This is just a way of saying, there's one element, another element, and so on. These guys here are numbers, the a's are numbers. I'm gonna write that down. They're called the coefficients of the polynomial, okay? N is a positive integer. So you start with n, then you have n minus 1, then n minus 2, all the way down to 0. This x, n equals 1, this is 1, and then 0, and then x is x, okay? So notice that there are no negative powers. This is important, okay? So P of x is a polynomial P of x that looks like this, where n is a non-negative integer. It could be 0, and then you only have a constant, a0. If n is equal to 0, then none of the things are here, and then you only have a0, okay? It's a non-negative integer. So you're not equal than 0. We call this the degree of P. Call the degree of the polynomial. Okay, this is the definition of degree, is that number n. And a0, a1, all the way up to an are real numbers. Now, this could be positive, negative fractions, whatever, okay? Just numbers. They could be 0 as well, okay? Are real numbers called the coefficients of the polynomial. Okay? Called the coefficients of the polynomial. And then this one right here, an, this is very important. We call this the leading coefficient. Notice that this is just the number that's next to the x with the highest power. Because notice that here the highest power is n. Everything else goes down. N minus 1, n minus 2, etc. Okay? So the highest power is whatever this number is, n. and then the number next to that term, the number in that term is called the leading coefficient. That is an important number. So a real number is called the coefficients of the polynomial. An is called the leading coefficient. And A0, we call it the constant term, because it's the one that has no x. But that's the leading coefficient is more important, so let me stress that. Okay? So An is called the leading coefficient. Notice that An is just the number that's next to x to the n. Okay? When you put this together, let me just define everything. Notice that a polynomial is just a bunch of terms, a bunch of monomials. So a term by itself is called a monomial. One of these things is called a monomial, just one thing. Mono means one. Okay? So it's a monomial. A polynomial is several monomials. You just put them together by adding and subtracting. So this one right here, which is the one with the highest power, is called the leading term. Okay? By the way, leading coefficient I will abbreviate by LC. And the term An times x to the n is called the leading term. And I'm going to abbreviate that one by LT. Okay? So in this definition, we have definition of polynomial, we have the notion of degree, leading coefficient, and leading term. And notice that once you know the degree and the leading coefficient, you can make the leading term. Okay? So note, the leading term has the form leading coefficient times x. So leading coefficient times x to the degree. Okay? So if you know the leading coefficient and if you know the degree, you know the leading term. Do you understand this? Because remember, this is An times x to the n. This guy right here is your leading coefficient. And this guy up here is your degree. Okay? So really, the degree and the leading coefficient are important information because you can use them to then make up the leading term. The leading term is going to play an important role in how the function looks like. The end behavior of the function. How you begin and how you finish your graph is encoded in this guy. The information is given here. Okay? What happens in the middle, then that's a zeros information that we're going to discuss next. Okay? But you need to first understand how to begin and how to finish your graph, and that information is here in the leading term. Okay, so the bottom line is, what's a polynomial? A polynomial is an expression that looks like this, that has variables, numbers. So only one variable, we're only dealing with polynomials in one variable. So when variables appear, the powers have to be nice, meaning they have to be non-negative integers. You cannot have negative exponents, fractions, nothing weird, denominators with x's in the bottom, nothing like that. Okay? If there is an x, it may appear by itself or to some number that's a positive number, like an x squared, an x cubed, stuff like that. Okay? That's what it means to be a polynomial. Every term has this form: a number times x to some positive number, or maybe no x whatsoever, just a number itself is okay. All right? But nothing strange. So I'm gonna give you some polynomials, and then I'm gonna give you some expressions, some functions. You tell me whether they are polynomials or not. Those that are polynomial, then you need to tell me degree, leading coefficient, leading term. Okay? So let's practice that. So example, determine if the function is a polynomial. If it is, find its degree, leading coefficient, and therefore, once you know degree and leading coefficient, you can easily tell me also what's the leading term. Okay? Remember, degree is the highest exponent that you see. Leading coefficient is a number in front, the coefficient of that term with the highest exponent. Okay? Whatever number you have in front of the x with the highest exponent. And then the combination of these, that term itself is called the leading term. Okay? All right, so let's do f of x equals 3x squared plus 3x minus 9. Then let's do f of x equals 2x to the 1/2 plus 3x minus 9. Let's do here f of x equals negative 2x times x plus 1 times 4x minus 1. And let's do f of x equals 2x plus 1 over 3x squared minus 5. Okay, so here we have four functions. Our job first is to determine which ones are polynomials, which ones are not polynomials. And those that are polynomials, then we need to find the required information. Okay? So let's just go through each of these and decide which one is and which one is not a polynomial. Okay? Let's see, number one. Is this a polynomial? Yeah. It is a polynomial. Does anybody understand this? Nothing strange happening. The x's, when they show up, they appear by themselves with a positive power, and they just have a number multiplied. Okay? No fraction, nothing weird. Okay, how about number two? Is this a polynomial? Yeah. Yes, it is a polynomial. Okay? Anybody think it's a polynomial, or you think something else? Yes? Why? Exactly. Remember what I said. No weird stuff happening. If an x appears, it has to have a positive number, like an integer as a power. You see, here n is a non-negative integer, and the powers are n, n minus 1, n minus 2, right? So all of those are integers. So no fractions, nothing strange, no negative number, nothing weird happening in powers. Here, that x to the 1/2 is not good. That's a function, but we are not interested in this type of functions right now. Okay? This is not a polynomial. And the problem is right there with that term. Okay? Also, for example, if this would have been like x to the negative 1, also that would have been an issue. If an x show up, it has to show up with a nice positive integer as an exponent. Okay? That's it. Okay, good. How about number 3? Is this a polynomial? So this doesn't look like the one in the definition, but notice that it says if it can be written in that form. So even though it doesn't look like that, if you were to multiply all of these parentheses, right, and expand all of this, eventually you can write this in the other form, right? Because the x's that will show up, they will just be x to some power, right? Like when you multiply these two, you get an x squared and all that business. You understand this? So this is a polynomial. In fact, this is the lucky case. If you manage to have a polynomial like this factor, then you basically know everything about this polynomial. Once it's like this, you will see it's very easy to graph. Okay? If it's the expanded version, the difficult part is to actually write it, the factor, to get it in factor form. This is the difficult part. In pre-calculus, you will learn how to do this in general for any degree. We know how to do it for degree 2, but when the degree goes higher, then it becomes really hard. At least with elementary techniques. And how about number 4? So in number 4, this is a fraction. The top is a polynomial and the bottom is a polynomial, but the function itself is not. Okay? By the way, this is what we call a rational function. These are the ones that we're going to study next. Okay? After we finish with this, next time, these are the type of functions that we're going to be interested in rational functions. But right now, we skip them because this is not a polynomial. Okay? Remember, if an x shows up, it needs to show up nicely with some power, but it cannot appear in the denominator, nothing like that. Okay? All right. Questions about identifying polynomials? Okay, so now now that we know that 1 and 3 are polynomials, let's find degree, leading coefficient, and therefore leading term. So degree, leading coefficient, then leading term. Remember, degree is the highest exponent of the variable. So what's the degree for number 1? Degree is 2. Good. What's the leading coefficient? 3. That's a number in front of the variable with the highest power. And what's the leading term? 3x squared. Do you understand this? Okay. About this one. Degree, leading coefficient, then leading term. So of course, when it's given like this, you can see it. But for example, if you have the polynomial factor, which is the lucky case, I guess the unlucky part is that you don't see explicitly what the leading term is. So you have to figure it out. Now, how do you figure this out? You have two choices. You multiply everything and you write it in the standard form, and then you're going to see it. Or just do what you need. Remember, we're only interested in the term with the highest power. So let's do this one at a time. So let's figure out the degree. What do you think is the highest power that we show up here after we multiply? 3. Does everybody see this? When you multiply this with this, you're going to get an x squared. That's the highest power there. And then when you distribute over this one, you get an x cubed. Does everybody understand this? X times x times x. So you're not going to get any power higher than 3. So the degree is 3. So you know that this is going to be equal to some number times x cubed plus all the stuff where that other stuff are lower degree terms. Does that make sense? So this is what we are after anyway. This is what we care about. This is what we're looking for right now. We already know the degree. Now I want to know what this guy is. The number. How can you find this number? How would you get this number? Just by multiplying, right, the leading coefficients of each term. That would be the number in front of the x cubed, because the number in front of the x cubed would be the product of the coefficients of the terms that you multiply to the x cubed, which is this one times this one times this one. Do you understand that? So when you distribute here, you have a negative 2x squared. Then when you distribute over here, you're going to have a negative 8x cubed. Yes? So that's negative 8. In other words, if your polynomial is factored, to find the degree, it's actually pretty easy. All you have to do is add up the degrees of each of the little factors. But you see, this is degree 1, this is degree 1, and this is degree 1. Yes? The sum, 1 plus 1 plus 1, that's 3. That's your degree. Similarly, if you want to find the leading coefficient, just multiply the leading coefficients of each of the little factors. What's the leading coefficient here? Negative 2. Here, what's the leading coefficient? And here, just multiply it. Negative 2 times 1 times 4. They give you a negative 8. Do you understand this? Okay, now once you have degree and leading coefficient, you can make the leading term. What's the leading term? Negative 8x cubed. All right, questions? Okay, so like I said, these guys right here, they guarantee the end behavior of polynomials. So let me actually explain that right now. Okay, end behavior. So note, we're going to talk more about end behavior for rational functions, but for a function f of x, for the function f, its end behavior, if you study calculus, then there will be another name that you're going to give it, that we give it to end behavior. A more fancy name is the limits are infinite. Okay? But basically, when we ask for the end behavior of a function, is what happens to the function when x is very big in the positive and in the negative direction. So when you are close to positive infinity, what happens to the function? Okay? When you start flowing in very big values like 1 million, 2 million, 1 billion, 1 trillion, whatever, what's the function doing? Is the function getting close to something, or probably it's going up, or probably it's going down? What's the function doing? Okay? Like for example, the parabola. What's the end behavior of the parabola? When x goes to positive infinity, y goes to positive infinity. It goes up. When x goes to negative infinity, y goes to positive infinity as well. So the end behavior is positive infinity in both directions, in both ways. To the left, to the right. Okay, so this is the kind of question that we want to look at now. So for a function f of x, its end behavior is the behavior of its y values when x is very large in the positive direction and very small in the x direction, and very small in the negative direction. In other words, when it's super negative, right? The more to the left you are, the smaller the number is in the negative direction. In other words, what happens over here and what happens when x approaches this way. The way that we write this, so very large in the positive direction, we write that by saying x, an arrow, and then positive infinity. So here we're saying x approaches infinity. So here we're saying x is very large in the positive direction. Okay? And then the way that we say very small in the negative direction, we write that by saying x approaches negative infinity. So you go all the way to the left. Do you understand this? So our job when we ask for the end behavior is what happens to the y when x is doing this kind of stuff. So that's why I was telling you, this will tell you how to begin and how to finish your graph. Because remember, you graph from left to right. So the end behavior tells you how to begin and how to finish. Okay? Then we need to figure out what happens in the middle, what happens in between. That's the zeros information that we're going to discuss. Okay? So for the function of x, its end behavior is the behavior of the y values when x is either very large in the positive direction or very small in the negative direction. So for polynomials, so theorem, the end behavior of a polynomial function is the same as its leading term. In other words, if you know the end behavior of the leading term, you also know the end behavior of the polynomial. And I guess I'm going to give you a sketch of the proof. Sketch of proof. And if I do it in general, then it could be a little bit confusing because of all the letters. So I'm going to do it with a concrete example, but it's exactly the same idea. Okay? So, idea via an example. Here is the idea. So suppose that you have a polynomial. Let's say our polynomial is, I don't know, let's say 3x to the 7 plus 4x to the 6 minus 5 x to the 4 plus 2x minus 1. Whatever. Just polynomial. Some x's and so on, it doesn't matter, okay? There is no x to the fifth. That's okay. The coefficient, that means the coefficient is 0. When a term is missing, that means the coefficient of that term is 0. Okay? You can think of an x to the fifth being here, but it has 0 in front. 0 times x to the fifth. So we just don't write. Okay, so what I want to show is that the way that this polynomial behaves, the end behavior is the same as this term, the leading term. Okay? And here's what we can do. To easily see that, what you can do is factor out this term. Okay? So the highest power, you can always factor it out. So I'm going to factor out x to the 7. Actually, I'm going to factor out the whole thing. I'm going to factor out 3x to the 7. If I do that, what do we get? I'm going to get 1 plus, now this is going to be a 4. I mean, I could leave the 3. Let me leave the 3 here, just to make it easy. So then this is going to be 4 over x. Make sure that you understand this. I'm taking out 7 x's. Okay? I'm taking out 7 x's. How many x's do we have here? We only have 6 x's. So there is one that we are left over. So that's why we need to divide by that. Notice that when I multiply, this cancels with this and get back my x to the 6. Do you understand this? So similarly, the next one, how many x's are we off? We're off by 3 x's, so I need to have an x cubed here. The next one, we're off by 6 x's, And here we're off by everything, so I need to divide by that. So when you distribute this x to the 7, you're going to get the line above. Do you understand this equality, that these two things are equal? Yes or no? Okay. Now remember, the end behavior is what happens when x is very big. So this is something else that will be important when we talk about rational functions. Let's see. What do you think is going to happen? Let's look at this fraction. 4 over x. When x is very big, let's say 100, 1,000, 1,000,000, etc. What's going to happen to this little fraction when x is very big? Yes?
It's going to get smaller and smaller.
So you understand this. If you have a fraction in which the top is fixed and the bottom just keeps getting bigger and bigger and bigger and bigger, that fraction is gonna get very, very, very small. Do you understand this? So for x large, for the absolute value of x large, which means x approaching positive infinity or negative infinity. When you do absolute value, it's a very big number. This approaches 0. Same thing with this one. Same thing with this one. Same thing with this one. So everything that has an x in the bottom is going to get very close to 0. Do you understand this? The bigger x is, the smaller these things are going to be. So what's going to happen to the whole parenthesis? The whole parenthesis is going to get closer and closer to this number 3. So this function is going to behave more and more like the function 3 times x to the 7. Okay? So this is for x large. So when x approaches positive or negative infinity, the function f looks like this one, and this is none other than the leading term. Okay? So that means when you want to analyze the end behavior of a function, just look at the leading term. That's going to tell you how to begin and how to finish your picture. So that's the reason why, before we continue with polynomials, we need to have a little chat about power functions. Okay? So wait, I have 3 minutes. In 3 minutes, I can do power functions because they're very easy. Okay? So before we look at polynomials in general, let's talk about this. This is called a power function. So this is an example of what we call a power function. So power functions, these are functions that have the form y equals a number times x to the n, and then we're interested with n being greater than or equal than 0. So when n is 0, y is a constant. Not interesting. We already know what it is, right? It's just y equals a. When n is equal to 1, y is a line. We already know what happens there. Now, the interesting thing is what happens when n is 2 or bigger. Okay? Now, when n is greater than or equal than 2, we're going to split it into 2 cases. N even, let me change the code. So n even and n odd. Okay? So when n is even, I'm going to do this one because the a is just, if a is positive, this is just a stretch or a compression. If a is negative, a stretch compression together with a flip. Okay? So a is really not important. What's important is the x to the n. When n is even, what do you think is going to happen? Well, this is going to look just like x squared. Okay? So when n is even, the power function is going to look like this. Of course, the higher n is, the steeper the graph is going to be, and the flatter is going to be the flatter. The closer to the x will be between -1 and 1. For example, this would be a larger n, okay, and so on. But if you look at it from far away, you still get that shape, okay, that U shape. And when n is odd, it's gonna look like x cubed when you look at it from far away. The important thing is that the degree here, even or odd, is gonna tell you the end behavior. So when n is even, what can you say about the y value? When x approaches positive infinity, or when x approaches negative infinity, what can we say about y? Positive infinity in both cases. And when n is odd, what can we say about the end behavior? When x approaches positive infinity, what is y? Positive infinity, it's going up. And when x approaches negative infinity, what is y? Negative infinity. Now, if you put a minus in front, like a -3 or something, this flips. So you have to flip this, okay?